Again to the DS Incubator. Today we start a new series about relational data. The goal is basically to help myself. I say here to help you understand, but in this audience today we have people who have more experience than myself in relational data. So it's mostly to learn about relational data and to be able to use it whenever we have a collection of tables that are related in some ways. So the series that I envision is not fixed, but I envision these 3 chapters. The first one today is about the basics of relational data. We're going to kind of define it and use dplyr to manipulate it. The second chapter could be about the package DM, which is an R package designed to define the data models and to work with relational data. And finally, to work with remote databases of the kind of data of, for example, SQL databases that even if you host them in your computer, well, they're being served and it works as if it was remote. So this is dedicated to just about anyone at 2 degrees and beyond who need to work with real world data. It's very rare that a data set, one single data set, has all the information that you need. Generally, the insights are spread across a number of tables usually, and that is why this is important. And it is to that collection of tables that are related to each other that we are calling relational data here. And the definition comes from the book Art for Data Science, which is the guide for at least this one chapter. Then we're going to be looking into different resources. So focusing specifically on the chapter of today, the objective is to understand what relational data is, also how to use different types of joins, understand what happens when a key has duplicate values, and we're going to define keys in a moment, and learn how to validate the keys to avoid join problems. So let's jump to the chapter of the day. So this is the repo that hosts the series. Let's go to the folder 1 dplyr to see the notes of today. So we're going to be working with dplyr. So I'm going to first attach it to my session here. Actually, I did it already, so that's done. Then we're going to be working with a toy data set and then a few graphs that Hadley Wickham wrote in his book. So this is the data that I'm going to be working with today. It is a collection of tables that totals a number of 2, only 2 tables, very small. It is intentionally designed to be similar to some data that we are working with in real life at 2 degrees. The table called companies has only 2 companies. They have a company's ID, number 1 and 2. So we have here information for only 2 companies. And there is a column called information. So for example, the company 1 is called Alpha. So Alpha sells solar panels and windmills. If we track the same ID in the other table, we can see that that number appears here in the table categories. And in the table categories, we have a column called sector. So the company number 1, which we know that sells solar panels and windmills, is categorized as belonging to the sector energy, which makes sense. And that's it. So just energy. And the company 2, who is called Beta, sells steel and also installs solar panels. They dedicate to very different activities. So company 2, as we can see here in the table categories, it belongs to metallurgy because it sells steel, and to energy because it installs solar panels. And then note that there is a third company for which we do not have data in the table companies. So this could be, for example, a problem in a real life data set that needs to be detected and then kind of addressed. So that's the 2 tables we're going to be working with. In a relational database, the relationships are always defined between pairs of tables. So any more complex relationship is always, can always be kind of decomposed to pairs, basically. One table relates to the other one, and then the other one might relate to another one. But every time you can decompose the complexity to just 2 tables, and they are linked by one column, as we showed before, the company's ID, for example, which these columns have a special definition and some properties that we're going to cover later. We call them keys, and there's 2 types of keys. So let me first, load that data. I'm going to show you live code just for a little bit, and then because there's quite a lot to cover, I'm going to just walk through the document. So here I'm defining the two toy data sets that I'm going to be introducing today. So if I type companies, we should see something very similar to what you saw on the notes. Here is that little data set with a key company's ID. I'm going to explain more about keys in a moment, and then the column information. And then the other table is called categories. So we should see it here. And here is where we have the sectors for each of those companies and a company that we do not have, right? So basically, the first, the most common way of joining two tables is with this dplyr verb called left join. In a moment, we're going to be talking about multiple ways of joining data, but this is the most common one. The left basically points to the table that we want to focus more on. I'm going to give more details later, but in this case, just to kind of give you a spoiler alert, we are going to be focusing on all the rows that companies have, and we want to add the columns that come from the categories table. So here we have the two tables, and we just call, we can do companies. We take companies first, and then, using in this case the base pipe, we do a left join with categories, right? And if you want to be explicit, which is the best practice, you should explicitly say which is the key variable using the argument by. So you say categories ID. So as you can see, not yet, but quite now, I may have category. Okay, so it's called companies ID. I made a mistake there, typo. So now you see that we have pretty much the same table. So we have the ID one that matches now the sector energy from the table categories, and now the ID two. The rows of appear kind of twice because two times it matches the sector table, right? So we're going to be talking about this now. So that is how it works. Basically, you take one table, find an appropriate join, and you join it with another table. And then you have to be explicit about which is the key variable that joins the two tables together. So from now on, we're going to spend time here in this document. So a more realistic example could be something like this. There is a data set actually that you can install. It's called Flight or New York Flights, I think. 13. It's a collection of multiple tables that illustrates a more real-life example, where you see there's a bunch of tables and they are linked to each other by some keys. In this case, for example, there's a table that contains information about different flights, and that table has one column that is called tail num, which is the number of the tail of an airplane that identifies specifically a plane, the machine, the plane, but there's no information there other than the ID of that plane. So if you want to learn more about that plane, you have to join the table planes, which then matches with that key tail number, and then it has more information about planes. So that's just to show how complex a data model could get. But that complexity should not be overwhelming, because every time, as we said before, the relationships are explained, or the relationships come down to relationship between two tables. So if you understand the relationship between two tables by one key, you have kind of moved forward in understanding the entire data model. So let's first overview all the possible joins that you can do, which is kind of interesting to know the options that you have, because sometimes they do come handy. In my case, I use so much that left join function that I kind of forget that there is other ways of joining data, and sometimes I find really awkward ways to do things that I could have done much quicker if I had this overview here more present in my brain. So basically, there is two types of join, broadly speaking. One join that mutates this is called a mutating join because it adds columns. Apart from matching rows, it adds columns, like the one that we saw a moment ago. We added to one data set, we added another column that came from another data set. And again, that is, you can split that in two. The inner join drops rows that do not match. We're going to see that graphically in a moment. And then we have outer joins that come with different flavors. Outer join is similar to the one that it includes the one that I showed before, that left join, and a couple of other flavors. So I'm going to discuss them, walking you through graphs before I explain more about them. So one big group, mutating joins, add columns, and then the second group, filtering joins, which do not add columns, or only deal with observations. So one is used to keep the rows in one data set that match observations in another data set, and the other one does the exact opposite. It drops all the rows in one data set that match rows in another data set. So let's use the beautiful graphs that come from that book, Art for Data Science, in the chapter Relational Data. Here we are introducing, looking into a graph that shows how to do an inner join. So if you use the function inner underscore join, this is what happens. So you have a table here. Basically, every time the arguments, to every function, every joining function are x and y. So we can think of this table here to the left, the one that has the values x1, x2, and x3, as being the table x, and then here to the right, the table y. You can see that the colors green with ID 1 and the color purple with ID 2, they match in the two tables. So an inner join, what we would do is to keep these two things together. So we glue these two tables by these two rows only that match, and then everything else is dropped. The result is the keys that we are using to match the tables, all the values that come from x, x1 and x2, and all the values that come from y. So this new column, val y, has been added. That's why it is a mutating join. There is an example here using the toy data that I used, but I think the images are a better fit for this relatively short demo. So if you want to come back to these materials yourself, then here you have some code examples, but I'm going to be focusing on the images. The left join is the one that I showed the demo for. It does also match the rows, in this case 1 and 2, in the two tables, but because we are focusing on the left, this table, we want all the rows, including those that do not match. By do not match, I mean, for example, the ID number 3, you can see there is no number 3 in table 1, y. So ID number 3 will match just a missing value, right? So the result will be that we get a match in 1, so we get the values of x1 and y1. Oops, I didn't mean to do that. Oh, that's interesting. Let me go back to here. Same for ID 2, so we get the x2 value and the y2 value because there is a value in both tables. But for the row with ID 3, note that we do have a value in x, and because it's a left join, we want that to be there, even when there is no match in the table y. And that is the most common because the inner join is kind of dangerous. Imagine if you're doing a big data analysis with a big table that you can't overview the whole table. It's very easy to drop rows that you don't know about, and you may be missing the reasons why the data is not matching. You may think that you may expect all perfect matches, and then if the data does not, you don't have a proof of that mismatch. So generally what you want is to get those NAs, those missing values, to then notice them and then explore why there was no match, right? So if you were expecting a match, maybe you want to have an NA, so you explore why it wasn't, and understand better your data. The right join is the same thing, except that now the focus is on the right-hand side. This is more like a convenience because you can always flip the table. So one table that was in the left, you can always put it on the right. But sometimes, if you're working specifically on a pipe, sometimes it's kind of nice to have the ability to call right join or left join. So basically, it's the same thing that we saw before. In this case, for example, notice how the key, the value of the key number 4 here on the right, which is the one that we are focusing on, has no match on X, but we still get it, right? We do not get number 3 because we are focusing on the right. But the full join does. The full join gets you every single row, right, and every single column. So you get that's why it's full. You get all the columns that come from X, all the columns that come from Y, and all the rows that come from X and from Y, even if there is no match. Okay, so it's a combination of the left and the right join. Again, here is one example for each of those joins. And now the idea of filtering joins. Filtering joins is a convenience to filter data based on another data set. So if you have a data set like X here, for example, which has keys 1, 2, and 3, and you happen to have another data set Y that has values in the key 1, 2, and 4, you may want to use that that Y data set to remove all the rows in X that do not match Y, right? Sometimes it is very convenient. Sometimes you can do it even with itself. You can create a smaller version of the data set and then match it back to itself. So in this case, what we get is only 1 and 2, but notice how there is no column value Y, right? So the filtering joins do not mess up with column. They don't add any column. They only focus on the table that you give to the X argument here, right? And you, in this case, in the actually I forgot to say this is a semi-join. That's the function that does this trick. So the semi-join, what it does is keeps the rows that match observations on the other table, as opposed to the anti-join that does the opposite. Wherever you see a match, like for example 1 and 2 do match from X and Y, and that's what you do not get. What you get is the other row that do not match the other table. And that's going to be handy when you want to validate the properties that you expect from the keys. I'm going to show that in a moment. So let's see what happens when a key has a value that is duplicated. That is something that does occur quite a bit, especially if you are working with a database that is not formally a validated SQL database, so, just data from the wild. So let's see, just try to understand what happens so you know what to expect. So here, for example, we have this table X that has, in the ID 2, it has two values. It has an X2 and X3. Both have the ID number 2. So when this number 2 in the ID will match the ID number 2 in table Y. So you would expect that because there is a match 2 times, that Y2 that comes from the table Y will be added in the 2 rows. Right? So basically you duplicate, you get a combination between the different rows that come from X and Y. So this is the case where the duplicates are only in one table, right? So here you can see the results. So X2 with ID 2 matched Y2, and X3 with ID 2 also matched Y2. So this is a way to inject those values of Y in X. But now there is also the case where the 2 tables actually have duplicated values, and what you get is the product. So every single combination. Actually, I think with Monica we used this recently in some code. I remember. I think last time we pair programmed where we created. We wanted to get all the combinations between one thing and the other, I think, and we did something like this. So here you see. The ID2 has a value in X2 and X3, and also on the table Y has Y2 and Y3. So you have all the combinations, notice here. So instead of getting 2 repetitions of 2, you get 4, because you have the X2 Y2, X2 Y3, X3 Y2, and X3 Y3. Kind of makes sense, but it's kind of nice to see it in a small, compact graphic way, so that when you get data from the Y in real life, you understand what's going on. Usually, a table is much bigger and it's a lot harder to see what's going on. So these are this next section is motivated by conversation with Miria. It is a step actually I need to do still in a project I'm working with right now. So we do have data and I need to validate the keys. So what does that mean? Okay, there is very few but important properties that keys need to have. For a dataset like companies, we define companies ID as the primary key, and that primary key has to have the property of having all values are unique. So all the values in a primary key should be unique. And one strategy to confirm that is to count the values of that primary key. So whatever is your primary key, you take the data set and count, called the function count, with the name of that candidate for a primary key, and you see if it meets the property that it should meet. So one way to notice if there is duplicates is then, in a very easy way, is to then call filter for values where n is greater than 1. So the count function will create a table that looks like this one here underneath, where you have only two columns, one that has the one column for the key that you are counting, and then one column for the number of times that basically that the values, the unique values of that column were counted. So if you filter by n, where the value of n is greater than 1, what you would expect from a properly behaved key is that you get a table that has 0 rows. So no values should be duplicated. That's what you expect. So that means that in the dataset companies, the column companies ID is a good candidate for a primary key. So let's just for comparison, the column companies ID also appears in the categories dataset, but note that if I do the same, I count company IDs in that table and then filter for n's greater than 1, I don't get a 0 row table, right? So that table cannot have company IDs as a candidate for a primary key. Another property that is kind of an extension of that is that no value of the primary key should be missing, because then what is it going to match, right? So one way to check for that would be to call the data that you're exploring, and then you can filter for rows where the candidate for a primary key is missing. So with the function isNA, you can do that. So is missing company IDs. If I filter for that, I should get a 0 row table, right? And then the final third property that is crucial to check is from the other table. So what you want to ensure is that remember that company IDs appear in that column companies, but also appear in the table categories. And there it was not a candidate for primary key because that table is valid because of the meaning of the data. It is valid that it could have multiple rows, right? So what it is, that is a column that all it does is holds a reference to the other table, to the primary key. So because the meaning of the value of those of that column is to refer to another table, it is called a foreign key, right? So the way what you need to validate for a key to see if it's a valid foreign key, you want to ensure that every single value that appears in a foreign key also actually is referencing an actual value in the primary key. So one good way to do that very quickly is the anti-join function. So remember we introduced that function before. Basically, anti-join, what it does is takes one data set, in this case to the left, and gets you the rows in the other data set that do not match. So what you would expect if it is a valid key is to get a 0 row table, because in that case that you could be confirming that every single row in your potential foreign key does match some value in the primary key. So in this case, the toy example is designed so that we do get a match. We do get that there is one row in the potential primary key that is not in the primary key, meaning that this data has a problem. So when these things happen, and they do happen in real life, you have to make a decision. You have to think and decide if you either drop that column, that row, or if there is any way that you can find that missing value in the primary key of the main table. In this case, it could be companies. All right, so that is all I had for this introduction to relational databases and how to work with them on dplyr. So I'm going to go back to your faces and hear from you. Let's see if there's any comment or question to share. Faria, go ahead.
This is more of a comment, but this was really nice tomorrow. This was like one of the DS incubators where I knew what you were talking about from before. So this was really good to review my knowledge. Thanks a lot.
Great, I appreciate it. I've read this chapter a long time ago, and I remember seeing those graphs and thinking, yes, I now get it. So I wanted to share it with you because the book is there, but sometimes you need either a reminder or be introduced to that so that people interested in learning more can get there. So hopefully this DS Inquirer would point people to that. I found it super useful. It's great to hear that you like it, Faria.
Yeah, thanks a lot.
Okay, if there is no more comments or questions, we are on time. So thank you all for joining me today, and see you next time.
Thanks. Bye.
Thank you.
Ciao.
Bye-bye.